Alright, in this video and the next few, we're going to be talking about the trans effect. And we're going to first talk about how to solve the problems. And I think the best way to do this is to go straight into working a problem. And then after we work a couple of these, we'll go into the theory about why the trans effect occurs. Alright, so what is the trans effect? First of all, it describes the position that an incoming ligand will attach to in a square planar complex. Okay, that's a basic way of saying it. The trans effect is only going to be applicable for square planar. Okay, so that's going to be a compound that looks similar to like this one down here. This is not applicable for tetrahedral, this is not applicable for octahedral or anything like that. It's only applicable for square planar complexes. So if you get a problem on your test and you see something that looks square planar plus a ligand, that probably means you're going to have to use the trans effect. So let's go over basically how to do this. The first point to understand, the incoming ligand, the location on the central atom here that it adds to is independent of the identity of this ligand. Okay, the identity of the chloride doesn't play a role with where it adds. Where it adds is dependent on the four ligands around the metal. Okay, so what you do is you're going to be given probably something like this. This is called the trans effect series. See how the direction of the greater than signs. Okay, so on the left-hand side, this is where it has the most trans effect, or the highest trans effect. On the right side, it has the smallest trans effect. So what you do is you look at the ligands here, chloride, ammonia, a nitro group, and a methyl group, and you see which one is farthest to the left. In other words, which one has the greatest trans effect. Well, just looking at this, it looks like the methyl is the farthest on the left, because notice, here's the nitro to the right of that. Here's the chloride to the right of that, and then there's the ammonia to the right of that. So the methyl group is the farthest to the left on the trans effect series. All right? So in other words, what that means is the ligand that's incoming will add trans to the methyl group. All right? So let's go ahead and do this. Let's go to Paintbrush. Copy that in. All right. So here's the problem right here. So again, what I'm going to say is which one of these ligands, which one of them was the farthest to the left? That was the methyl. Okay. All that means is the chloride over here is going to add to the position trans to the methyl. Trans just means right across the metal from whatever we're talking about. So that means all I'm going to do is I'm going to just draw it like this. Chloride's still there. The methyl group is still there. The nitro group is still there, and this ammonia is going to be the one that's displaced, and I'm just going to put this chloride right there. And we're not really so much concerned here about the overall charge, although it does go down by 1 because ammonia is neutral and chloride's negative, so this is now going to be 2 minus because it originally started as a -1. The point is, though, is that the way you solve a trans effect problem is you look and find the ligand that is farthest to the left on the trans effect series. If your order was reversed, just understand it's the one that's the greatest, the highest trans effect. In this case, it's the methyl group, so that means that the ligand is going to add trans to that group, so it has to add right across. And that's why the incoming ligand went there. All right? So hopefully that makes a little bit of sense. And that's the basis of the trans effect in terms of solving the reaction problem. All you do is you find which one's farthest to the left on the trans effect series, or which one has the greatest trans effect, and then you just add the ligand right across on the trans side from that. All right. One thing I wanted to point out before we conclude this video is that this trans effect series, notice, is not the same as the spectrochemical series that you might have seen earlier in inorganic. Those are different lists, so understand they're different. All right. In the next video, we're going to go over another trans effect problem, and we'll see if we can figure this one out. All right, so make sure to like this video and subscribe for future videos and notifications. Thank you.